Hello friends, and welcome to CMake for JUCE developers. This is a new video series that Josh and I have been discussing for a little while. We thought it would be great to create a series of video tutorials on creating a CMake project from beginning to end that is tailored specifically to JUCE developers converting to CMake from using the Projucer. If you are already using CMake, there still may be some good information for you in these tutorials, or at least I hope so. Um, but this is really tailored to JUCE developers transitioning from the Projucer, both like convincing you like why it may be necessary and also kind of showing you how CMake is similar to some of the workflows that you may already be familiar with. The first video in this tutorial is why CMake. This is going to be a discussion of why you should care about this tool, why you may want to convert to using CMake if you're not already. I definitely understand having a bit of trepidation there. You know, if you've already got your build system up and running using the Projucer, I think there's kind of an attitude of like, you know, if it's not broke, don't fix it, don't touch it, just kind of like leave it be around build systems, which makes sense. And I also understand the fact that it requires time investment. And as programmers, our time is our money. So I definitely understand there being some trepidation around switching to CMake, but hopefully this video will convince you that the benefits outweigh the cost. CMake can improve every part of your development process, and I would make the argument that if you're not using CMake, you have some built up technical debt that is only going to continue to accumulate the longer you wait to transition to CMake. Before I go any further, I just want to take a moment to introduce myself. My name is Ben Vining, if you don't know me. I am a self-taught C++ developer. I used to be a musician and I used to work in theater, and during the 2020 pandemic lockdown, I kind of dove headfirst into making plugins with JUCE. And I kind of, along the way, I discovered CMake and I kind of dove into CMake as a topic because I was really interested in this idea of perfecting the build system itself. And I'm going to kind of discuss that along the way, but I do believe that CMake is also a great way to learn more in depth about C++ as a language and how a C++ build actually works. So I'm going to discuss each of these topics individually throughout this video, but just as an overview, CMake provides maintainability and future-proofing for your projects. So maintainability, it's much easier to kind of dry up your code in CMake. And because CMake is actually code, there are various strategies you can use to debug it, similar to C++ code, which I will go into later. And future-proofing, CMake has a very, very strong focus on backwards compatibility. So you can write your build description for your project today and leave it alone and come back in 10 years from now, and you should be able to compile it without making a single change to the CMake scripts, as long as the source code hasn't changed. But you can upgrade the compiler, you can change the back end being used. You know, maybe you were using makefiles before and now it's Xcode or some new IDE that gets invented, and CMake has created a back end for it, and those are all things that are abstracted away for you by CMake, so you don't have to make any actual changes to your build description. CMake can simplify scripts on CI. Configuring your build and running your build, CMake allows you to kind of abstract those steps away and just use CMake itself, as opposed to having to have specific knowledge of, like calling Xcode build or MS build or anything like that. CMake is one tool to rule them all. Or really what I should say is that it's one build description to rule them all, because CMake is actually not just one tool. The CMake executable itself generates build files and can run the build, but CMake also provides tools for running tests and creating graphical installers for end users. And the build description files that you write to run your build can also include setup for tests and for installer creation, which is very convenient because having all of that in one place makes it much easier to kind of integrate them together and keep everything organized, which I'll elaborate on later. But the point here is that all of these things are kind of integrated and centralized by this one multi-paradigm tool set. And also something that I'll talk more about later, CI can be faster if you use CMake. Both setting up the CI environment and actually running the build, there's multiple things that you can do to kind of speed things up. And so this is one example of how I mentioned before that using CMake can actually save you money. That's quite literal in this sense because CI minutes can get pretty expensive pretty quickly. And CI can be much faster using CMake than using the Projucer. So the first thing that I wanted to talk about is the similarities between CMake and the Projucer because there's often a lot of confusion around this topic. So I mentioned on the last slide, I kind of talked a little bit about like, the back end that CMake uses, what if it was Makefiles or Xcode, and CMake is similar to the Projucer in this way. They are both build system generators. So the Projucer itself is not a compiler. What it does is you describe how to build your project, and then you hit the button that says export and open in IDE, this button right here. And what it does is, so I've selected Xcode here, and it will actually save this as an Xcode project and open Xcode. And CMake is the exact same way. So I'm in one of my repositories here, and if I just call CMake-b builds-g Xcode, what this means is -b is the builds directory, so you can see here it created a folder called builds, and -g is, I'm telling it I want an Xcode project, right? And so that's basically the same as this drop down here in the Projucer. And as we can see, in the builds directory, it's generated me this Xcode project file. And so there's often some confusion around this. People say, well, I need Xcode projects. I don't want to use, CMake's, whatever. But the point here is that CMake is not actually a compiler. It doesn't actually ship with a build system. It generates build files for other build systems. So here I've generated an Xcode project, but I can just as easily create a Makefile that will do this. And as you can see here now, what I've got is I have a Makefile in my build directory. And right away, this is one advantage of CMake over the Projucer, because here in the Projucer, you have to separately define every exporter individually. But in CMake, there are no actual code that's specific to the generators. All you do in the actual code is you just describe, this target is built from these source files and it has these sets of dependencies. And then on the command line with this -g parameter, on the command line, when you actually invoke CMake, you select the generator. So the person writing the CMake build files doesn't have to know what generator you're going to use. Whereas in the Projucer, you have to actually, the person creating the project has to set up each individual generator in order for you to be able to use that build system. And so, so both CMake and the Projucer create build files for another build system to use. They're both capable of generating project files for Xcode, Visual Studio, Makefiles, things like that. And they actually both have GUI editors. So obviously the Projucer is a GUI application here, and I believe you also can use it from the command line, although I'm not as familiar with that. But obviously the Projucer has that GUI interface. And then here, this is CMake's GUI editor. the difference between this and the Projucer is that the Projucer's GUI editor is much more um, geared toward the developer's experience, right? So the person writing the project, this is very like you have fields you can fill in here, and it's very kind of like an interactive experience for the person creating the project. The difference here is that the CMake GUI editor is more focused on somebody using the project, right? So basically, the purpose of this editor is for you to be able to look at all the different configuration variables and change them, right? So this here, this limes build tests, where that actually comes from is in my CMake script here. I have an option. There's a command that says option limes build tests. And in a future video, I'll go into this in a little bit more detail. But the point is that this is all of these values here are variables in the CMake scripts that affect the way that CMake runs and generates the build system. And you have a user-friendly graphical editor for this. And, you know, if it's a Boolean, it gives you a check mark. If it's a file path, it gives you a file chooser here, you know, stuff like that. So they both have GUI editors, the difference being that CMake is a little bit more geared towards somebody building the project, and the Projucer is more geared towards somebody writing the project. Differences between CMake and the Projucer. Probably the most crucial difference and the most fundamental difference is that the Projucer is essentially collections of data files, whereas CMake is actually code. So like I said before, the Projucer has this GUI application where you can populate all the different fields, and then when you actually save the Juicer project, what it is an XML file that contains all of this as static data. And CMake, on the other hand, is actually code that when you invoke CMake, like I showed you, to generate the build files, it's actually an interpreter that runs your code, and so you can have if statements, you can have for loops, you can do sophisticated things. People have, you know, just for fun, somebody actually wrote a ray tracer in CMake, which I found a while ago, which I don't recommend you do. But the point is that CMake is actually a full-fledged interpreter, which some people view as a downside of CMake, because it is true that it can introduce some additional complexity. But I view this as an advantage of CMake over the Projucer, because it allows you to do more sophisticated responses to your build environment. And it allows you to have some more sophisticated options in your build. Like I showed you in the graphical editor, you can have, you know, options, and you say, if the user wants this thing, then do this in the build, otherwise do this, which would be relatively difficult to implement in the Projucer. Another difference is that CMake is an industry standard. Pretty much anyone who is a professional C++ developer has probably at least seen a CMake file before, and the vast majority of repositories out there will have CMake support, and the vast majority of package managers available for C++ out there have CMake support, and some of them are actually written in CMake. And the Projucer is a tool that has its uses, but it is relatively contained to the JUCE environment. There's not really a reason why you would use it for anything non-JUCE, and outside of the JUCE community, people aren't really very familiar with the Projucer and how to use it. So if your project only has a Projucer interface, it may be more difficult for someone to integrate it into another project that is being built with a different system like CMake. Whereas if you provide CMake build files, then there's a very, very good chance that that's pretty much all you need in order to be able to integrate it into any other system you want. Because CMake is pretty much a de facto industry standard. Another difference is that CMake is completely OS and build system agnostic. So within the Projucer, you can configure builds for different OSs, but you have to configure each one specifically, right? So you have the exporters tab, and you have to create an exporter for Mac OS Xcode. You have to create an exporter for Windows Visual Studio, and you have to create an exporter for Linux Makefiles, right? And I think that that is a disadvantage because you have to explicitly create each one of those exporters, whereas in CMake, it's completely agnostic of what OS it's running on and what build system is being used. So all you have to do is you just describe, how to build what you want, and then when the person actually invokes CMake on the command line, they can specify what generator, and then obviously CMake knows what OS it's running on, and so under the covers in the back end, it takes care of all the specific implementation details for you. And as you're writing a CMake project, there may be reasons why you want to do certain behaviors if a certain compiler or a certain build system is being used, and that is also possible. But for the most part, CMake build descriptions should be entirely OS and build system agnostic. And in general, I would say that a well-written CMake project should be able to be compiled with any generator, meaning build system, so Xcode, Makefiles, Visual Studio, but also any compiler, right? So you should be able to use Xcode build with Makefiles, or Xcode with GCC, or Visual Studio with MSVC, or Clang, or GCC, or, you get the point. The idea is that you can kind of mix and match, and it's really up to the person building the project to use the toolchain of their choice. Okay, so my first big bullet point about CMake is maintainability. And where I think CMake really shines is you don't have to repeat yourself very much. So, for example, if you have a similar set of build configuration settings that you use for a lot of projects, like maybe you have some standard compiler options, some standard, whatever it may be, in the Projucer, there's really no way to get around copying and pasting those configuration settings into every project. Whereas in CMake, you can put them in one script in one place, and then every project can include that script and maybe call a function or just, bring it into their build in some way. And that makes it much easier to maintain, because making a change, you can change it in one place instead of having to change it in every single juicer file that you have, right? And in addition to project setup like that, this also applies for managing source files. So I've seen JUCE workflows before where, you have multiple projects, and then you have some shared code that is used in multiple projects, and it may be in a subdirectory, and so each of these projects' juicer files has to explicitly list out every single file in these subdirectories, and that again is not very maintainable, because if you want to add a file, suddenly you have 10 minutes of work in front of you adding that file to every single juicer. Same goes with removing a file. And whereas in CMake, every directory can manage its own files. So you can, from the top level project, you can just say, okay, bring in this subdirectory. And the subdirectory itself can populate what it needs to into the build. And the top level project doesn't need to have any specific knowledge of what's in that subdirectory. And so it becomes much easier to make changes only to one node of a build graph instead of kind of having everything defined at the top level. Excuse me. I will make a note that JUCE does provide a way to encapsulate shared code in the form of if you write your own JUCE modules. But there are also some downsides to this approach, which I'll go into in more detail in a future video. But the biggest downside is that JUCE modules are recompiled every single time for every project that uses them, even if it's the same exact code. And that's just how the JUCE build system was designed. There's really no way to get around that. And so if you have a lot of shared code that is the same in every project and doesn't need to change, then I would suggest compiling it into a shared or static library, because then it can just be compiled once and linked to from every project. And again, that's something that I'll go into in more detail in a future video. But yeah, so both managing source files and the actual build description, CMake allows you to not repeat yourself and to keep things more encapsulated and contained. And this is pretty much what I just mentioned. Encapsulate knowledge of files to where those files actually are on the file system. So in the Projucer, if you're not using JUCE modules, then you maybe have, some sort of path basically hard-coded into your Juicer file, which is pretty fragile across OSs and across different build environments, because you may start to be making assumptions about how a user has their workspace configured, which CMake has ways to abstract that away and not really need to hard code things like that, which I'll go into again in the future. Future proofing. So as I've already mentioned, in the Projucer, if you want to support a new build system, you need to explicitly create an exporter for that. And this is something that I personally have experienced recently, where one of my contracting gigs, they wanted me to add an exporter for Visual Studio 2022. And it was a surprisingly big pain, because you have to basically copy and paste all these values from one exporter tab over to the other, and then make sure you didn't make any errors, and it becomes basically a game of maintaining large text files as hard-coded data, as opposed to with CMake, changing from Visual Studio 2017 to 2022 involves no changes to the actual build description. The only thing you need to do is, when you're going to create your build files, you invoke CMake with -G Visual Studio 2022 instead of 2017. And it should just work out of the box. And so it requires no changes. And this is going back to that point I made earlier about saving you money by saving you time. This is something that not only makes your projects more versatile for the end user, somebody who wants to build it, they can use whatever tool they choose, but also for you, if you need to upgrade your compiler or upgrade your Visual Studio, it can be a 2-second thing instead of an hour or more of copying and pasting and checking, and it can really save you time. Excuse me. So like I mentioned, CMake's command line at generation time allows you to specify what generator to use. And you can also change compilers and things like that. And CMake has a very strong focus on backwards compatibility. So like I mentioned before, there's a pretty good chance that if you want to write your CMake files today, I would be willing to bet that you can come back in a couple of years and, with the newest version of CMake, compile something that was written for a very old version of CMake. They actually have this whole system of, in your build description file, you declare, this is the version of CMake I'm writing this for. And they have this whole system of, if it's an older version, and the CMake that's processing it is newer, then it will actually change some of its behavior to match the way that the old version worked. to make sure that nothing is like breaking on you unexpectedly. So that's something that I'll go into more depth on in a future video, but the takeaway here is that CMake has a very strong focus on backwards compatibility, and that you should feel very secure in that. They take it very, very seriously. CMake simplifies scripts. So I've mentioned this syntax here of -b builds, or whatever build directory, and -g, and you can choose your generator. And what that command does is it generates the build files. So that will create you a make file or an Xcode project or a Visual Studio project, something like that. But CMake also has this command --build, right? So CMake, after it has generated your build files, it knows how to invoke the native build tool for you. So something that I've seen in many JUCE projects is they'll, in your CI, you might have something that actually invokes Xcode build or MS build or make, and that's completely not necessary. You can just say to CMake, okay, build, using the files that are in this build directory, and it will do that for you. You don't need to ever directly call Xcode build or MS build or anything like that. And as I mentioned before, CMake also has utilities for running tests, for installing, and for creating graphical installers. I'll go into each of these topics in more depth later, but the takeaway here is that CMake's command line interface is designed in such a way that you really only need to specify platform-specific things in the generation command, the first one at the top here. And everything after that can kind of just reference those build files that were created and abstract away the entire process of like building or installing or anything else that you want to do with those files, which can really greatly simplify your scripts, because now instead of having to have one build script for Windows, one build script for Mac, one build script for Linux, you can just have one script that runs CMake with the appropriate generator for your platform, and then calls CMake --build, ctest to run all your tests, and then cpack to create an installer for you. And on the topic of CI, building the Projucer itself takes time. Sometimes it takes longer than the actual build of your product, because it requires you to compile most of JUCE itself just to build the Projucer to be able to compile a JUCE project. And if you're going to download a pre-built binary of the Projucer, then that requires hard coding a URL into your scripts, which again can be kind of fragile. Whereas CMake, because it is a de facto industry standard, it comes pre-installed on most CI services. And if you're using a CI service where it doesn't, then I think you should file that as a bug. And also, if you want to be very specific about using a certain version of CMake, there are usually pre-available like actions, or whatever your service calls them, because I use GitHub Actions, and there's like a community, somebody has made an action that says, okay, download and set up this particular version of CMake. And those things are also available for Jenkins and many other services. And also on the topic of CI, Ccache is a compiler cache. And what this does is whenever it wraps compiler commands, right? So basically what you do is in CMake, you tell CMake, I want to use Ccache as the compiler launcher. And so it basically intercepts all calls to the compiler, and Ccache looks at it and says, have I compiled this source file before? And if so, have any changes been made to it since then? And if any changes have been made, it recompiles it. But if not, it just reuses the past output and does not recompile the actual source file. And this can really, really come in handy for CI, because you can have a very, very large project, and if you're only making incremental changes, then even if your project is very, very large, you can have CI runs just, take a few seconds because it's really only recompiling what has been changed. And this is something that is fairly easy to set up in CMake, and as far as I know, is really not even possible in the Projucer. So this is a pretty big point in favor of CMake, in my view. Code reuse and shipping. This is something that JUCE developers may or may not really be interested in, because what I'm talking about here is if you're developing a library or if you want to use somebody else's library, and it's very possible that your code is just the JUCE code, and maybe you have some internal shared code of your own, and maybe that's it. And if that's the case, then what you should really be concerned about is reusing your internal code across any projects you have. And as I mentioned before, it's possible in the Projucer you either need to deal with like listing out all the files explicitly or make a JUCE module. But if you do that, then it gets recompiled every single time for every single project, even if it's not changing. And so this is something that CMake can help you with, because you can just create a C++ library and compile it once and then link it into every one of your projects. And again, CMake provides user configurability. So that graphical editor that I showed you earlier, if you have, some options for your library, like, maybe there's some sort of optional dependency that you may or may not build with, and CMake makes it very easy to define those things as you're invoking it. So at generation time, you can pass in, various configuration options before you build. Now, you may or may not find this one applicable, but if you're going to be worrying about integrating third-party libraries into your code, with the Projucer, it's basically hard-coded. So you basically tell the Projucer, these are the names of the libraries I need, and what it does is it generates the linker command line and just says, L lib A, L -L lib B, and then you can hard code into the Projucer a library search path. And that's fine to some extent, but there are many cases in which that may not be really like the most stable or the most desirable behavior, because in CMake, if you're going to integrate a third-party library, you can not only not have to hard code the path, you can like dynamically find it on the system, but you can also deal with the version and the configuration. Like maybe there are different binaries produced by this library for debug and release, and you can link to each of those for those specific configurations. And another use case that CMake supports is that you can either use a system install of a library, or you can point it to somewhere where it can find a pre-built binary, like maybe a cache that's local to this project or something that's not on the system-wide library path. Or you can actually build these dependencies from source if you want to. And the cool thing about this is that as far as the consuming CMake project is concerned, you don't really even need to know whether it's a pre-built binary or it's being built from source. All you need to do is tell CMake, my dependency is this library. And then the person building it can either say, okay, so to find that dependency, use a system installation, or use this binary I'm pointing you to, or go fetch it and build it from source. And those things are all configurable from outside the project. So the person writing the project can simply declare the dependencies, and then the person using the project can resolve them as necessary for their specific environment. So it's much more configurable and user-friendly in that way. Another thing that CMake allows you to do is tooling integrations. There are various static analysis tools such as Clang Tidy, CPP check, include what you use. And what CMake will do is it will actually run these tools with the actual compilation. And so you'll get the output from these tools as you're building, which again, the user building it can turn this on and off from outside the project. But it's very, very useful because you can then have all of this, output without needing to run these tools in a separate step or with a separate script. Centralizing your scripts. One build description to rule them all, as I mentioned at the beginning. So CMake is great for building for many reasons, but it doesn't just stop there, because CMake has utilities to run your tests, to build documentation, to create installers, and all of these things can be configured in the exact same place as the actual build of your code, right? So you don't need to have a separate script that configures your installer. One really common workflow that I've seen in the wild is people having, a script that will build the Projucer and then call the Projucer from the command line to save their project, and then call either Xcode build or MS build or make to build their project, and then they have separate scripts to create installers, one for Package Maker for OS X and one for NSys for Windows, and they basically just kind of replicate the installer like look and feel in both of those scripts. And again, that's something that CMake can abstract for you. In your CMake configuration, you can just say, take this target you've just built and create some install rules for it. And then you can run their CPack tool to create a graphical installer for your platform. And the cool thing about CPack is that it uses the same generator concept that CMake itself does. So in the way that CMake has, you can just kind of write an agnostic description of what needs to happen and then create different generators like Makefile or Xcode or whatever. CPack does the same thing. So you have an agnostic description of what things get installed, and you can define components and installer types and all these fancy features, and then you can just tell CPack, okay, make a package maker installer from this, make an NSys installer from this, and it also has support for like deb and RPM packages and things like that. So it's a really, really powerful tool, made all the more powerful by the fact that you can define those configurations right next to the actual build. So not only does it centralize your code, but it also, again, allows you to kind of not repeat yourself, because you can create your install rules right from the targets. So you can, have your application built, and you can just say, take this application target and create install rules for it, and put it in this component, and put this other stuff in this component, and you get the idea. Documentation can be built using custom build commands. So CMake allows you to add anything executable as a custom command to the build system. So documentation is one really common use case of this, because you can locate the Doxygen executable, or if you use Sphinx, you can do the same thing. And then you can add a build command that when that target is built, it basically just executes Doxygen or Sphinx or whatever you're using over your source code. And I'll do a video on this topic later, but again, it has the same advantages that everything else does, because CMake has internal mechanisms for locating programs on your computer, so you don't have to hard code anything, and it can be configured from outside the project. if there's for any reason like a special path to Doctogen that somebody wants to use, they can kind of inject it from outside, but your build command will still work because it just knows, whatever Doxygen is being used for this project, it can execute that as a build command. Same thing with tests. Anything executable can be added as a test. And so the typical way that you do this is you create some sort of command line executable which runs all your tests, and then you can just say, all right, as a test, execute that executable, which becomes really convenient because CMake allows you to, instead of specifying a path, you can just specify the name of a target. And so if you're already configuring your command line executable to run your tests in your CMake, then you can just pass the name of that target to a test command, and it will automatically take the path of what it built and put it in there. So you don't even have to really know or care about that. CMake handles all of that for you. And the last major bullet point that I wanted to talk about is that CMake will help you learn. As somebody who, I mentioned at the beginning of the video, my first introduction to the world of C++ was JUCE. And so for a while, it just kind of seemed like this magic little playground, that had been kind of set up and everything was working, and I wasn't really sure why or how. And it wasn't until I started kind of going outside of the land of the Projucer and JUCE modules that I really started to learn more about the details of compilation and linking, like what a translation unit is, things like that, types of libraries, shared or static, symbol visibility. So in the JUCE source code, there's a macro JUCE API in front of every class name. What does that do? Why is that there? This is a question that using CMake will help you learn, which goes hand in hand with ABI, Application Binary Interface, which has to do with how libraries that you link to actually interface, like, how their types are laid out, things like that, so that you can communicate properly across the boundaries of libraries and executables and so forth. And all of these things are topics that I will talk about more in depth in future videos, but I just wanted to point out that I believe that using CMake causes you to gain a deeper understanding of C++ as a language, the C++ build process, and maybe have some kind of revelations about C++ that you may not have had otherwise. And the other point here, especially with symbol visibility, like I mentioned that macro, like the way that you design your build system will affect the way you write your source code. And that is something that I think goes pretty understated because, for example, if you are using the workflow of using the Projucer and not having JUCE modules, and so you're listing every file individually in all your Juicer files, that may cause you to kind of not really want to add new files for things, right? And so that may cause some of your files to get pretty bloated and less focused, and that's a result of your build system affecting the way that you're deciding to organize your source code, which makes sense. The build system should kind of be reflected in the way the project is organized, but it shouldn't be a deterrent to letting things be well organized. The build system should help you and not really hinder you. And for all of the reasons that I have just outlined, I believe that CMake is the best choice currently available for C++ build systems. And I believe that if you are using the Projucer and not CMake, I would make the argument that you have some technical debt that will continue to grow exponentially the longer that you wait to transfer to CMake. So yeah, that's everything that I wanted to cover for this video, and that hopefully gives you an overview of where this series will be going in the future. And thank you for watching.